So students, in previous part we have studied till the classification of p-type and n-type extrinsic semiconductor. Today we are going to study what is the difference between n-type and p-type semiconductor is exactly. If we consider n-type extrinsic semiconductor, then it is obtained from intrinsic semiconductor by simply addition of pentavalent impurity. The example of pentavalent impurity is antimony, phosphorus and arsenic. By using one of the group 5 element in our periodic table, group 5 element means these elements are having 5 outermost electrons in their outermost shell. That's why when these electrons are added to the intrinsic semiconductor structure, then there is always one valence electron left, and then this extra electron will revolve in semiconductor structure to give extra current to flow in particular material, that is in that n-type extrinsic semiconductor. Same thing happens with p-type semiconductor also. In case of p-type semiconductor, trivalent impurity atoms are added to intrinsic semiconductor. The examples of trivalent impurity atoms are boron, gallium and indium. These are group 3 elements in our periodic table having 3 outermost electrons in their outermost shell. The next difference between n-type and p-type semiconductor is that when impurity atoms are added to the intrinsic semiconductor, such atoms which are from pentavalent impurity atoms are called as donor atoms because they donate one extra electron to the semiconductor structure. That's why they are called as donor atoms. And on other side, for p-type semiconductors, the impurity atoms are added, create vacancies. There is no possibility of extra electron here, but extra hole is created. Hole means it is a vacancy for an electron, and these holes are having opposite charge of electron. We know electron have negative charge, but hole must have positive charge on them. That's why they attract electrons and become stable. So this is how p-type semiconductor impurities are called as acceptor impurities. And the third difference is that the electrons are majority charge carriers and holes are minority charge carriers in n-type semiconductors. As number of electrons in the process of doping becomes increase, that's why n-type semiconductors are called as having electrons as majority charge carriers. And for p-type semiconductor, majority charge carriers are holes and electrons are obviously minority charge carriers. So what is meant by acceptor impurity level and donor impurity level? We have already seen that p-type semiconductors are created by acceptor energy levels and n-type semiconductors are created when donor energy levels are created. So the position of acceptor energy levels is just above valence band, while donor energy levels are created just below conduction band. P-type semiconductor have large number of holes, and the position of these holes is seen in valence band, and minority charge carriers electrons can be seen in conduction band. In first diagram we can see that directly. And on the other hand side, n-type semiconductor have minority charge carriers electrons but holes as minority charge carriers and electrons as majority charge carriers, which are seen in conduction band. So these are acceptor and donor impurity levels, and the name is given by donor atoms and acceptor atoms respectively. Now we have to study tetrahedral structure of silicon. As we can see, silicon is having valency of 4. That's why we can say that there are 4 electrons in the outermost shell of silicon. So these electrons will make covalent bond with their neighboring silicon atoms, and then silicon structure become stable. Now we can convert this intrinsic semiconductor atom to intrinsic semiconductor atom by simply replacing pentavalent impurity or trivalent impurity, so that we can make them extrinsic semiconductor. There are two types of extrinsic semiconductors, N-type and P-type, which are made just by replacing pentavalent and trivalent impurity respectively. If we replace one silicon atom with one pentavalent atom, then we get N-type extrinsic semiconductor, while if we replace one silicon atom with one trivalent atom, then we get P-type extrinsic semiconductor. That we have to understand here. So what happens actually here, if we take example of lead as pentavalent atom, which is having 5 valence electrons, they will make covalent bonds with neighboring silicon atoms, because silicon is a intrinsic type of semiconductor. Covalent bonds formation will happen only with 4 electrons of lead. The symbol of lead is Pb, which is shown at the center in first diagram. So Pb is lead which is added as an impurity, and then one extra electron is left. That donor impurity contributes free electrons. So that free electron will tend to constitute a current in semiconductor structure. Similarly, in case of P-type semiconductor, boron is taken as trivalent impurity, which is added in structure of silicon, intrinsic structure, and if we replace boron with silicon atom, it will create only 3 covalent bonds with neighboring silicon atoms. But there is one extra vacancy for electron left always whenever we add trivalent impurity in such structures, and that vacancy is called as hole. So it results in formation of acceptor impurity level in the band structure of P-type semiconductor. So the next point we are going to see is p-n junction. We will see that point in next part. Thank you.